Hello everyone, my name is Dening Luan. Today I will introduce my final year project, the Low Density Parity Check Code in Wireless Communication. The project is to simulate the low density parity check code in wireless channel and analyze its performance with different parameters. This video contains a brief summation of the theory and implementation of each component in the low-density parity check code system, which is applied in the wireless communication environments. The simulation of the system is based on MATLAB, and it can be divided into 5 important components according to the function and mechanism. Firstly, the parity check matrix is a preparation of the simulation. Then, it is the encoder and the decoder. Between them is the OFDM modulator and demodulator, as well as the feeding channel. This is a block diagram of the system. The bit error rate is calculated by comparing the input and output. This is also the structure of the MATLAB program. Before introducing low-density parity check code, let's have a quick look of how a common linear code works. Firstly, there is a generator matrix G. The identity matrix for message bits and the matrix P for parity check bits. The parity check matrix H is a transform of G. Then we use H to calculate the code word. After passing through the channel, the code word is added with noise. The noise has the error pattern of E. The syndrome is then calculated. If the syndrome can be found in the code set as EJ, the error can be corrected. This is a hard decision decoder, but actually, we use soft decision to improve the performance in later chapter. This is a telegraph of 7/4 Hamming code. The benefits of telegraph is that we can clearly see how information travels between bit node and check node along the edges. In particular, we hope the cycles to be as long as possible, so the error on each bit are weakened in loops. It has more probability to be corrected. There is an example of short cycle. The shortest cycle is a 4 cycle. The error is centralized in each iteration and spread in the whole decoder. We never want this to happen. The design of the generator. Firstly, we randomly built a low-density matrix. The process of allocating ones for rows and columns are separated, since we need it to be sparse for both. Then we need a program to detect 4 cycles and flip some of the ones in a cycle to remove them. This is the output of the generator. It is very sparse and contains no 4 cycles. As I have mentioned before, if we have the parity check matrix H, we need to get G for encoder based on H. The simplest method is to use LU composition and make G in the following form. The identity part is for message bits, and the matrix P is for check bits. There is a more popular method called approximately lower triangular form. Firstly, we are given with the number G, which can be as small as possible. Then, we clear the northeast part of the matrix, and T becomes the lower triangular matrix. As we know, row and column permutation is equivalent to multiplexing a transform matrix. We want to transform E to 0 and here is the transform matrix. We suppose the code word has the following format, and we can finally get the presentation of the two parts of the check bits. This is the generator matrix of the two different encoders. We can observe that the first one is not sparse anymore, since we encode by using m plus g. The complexity of the first encoder is O(n) squared, while the second one is almost linear time. The basic idea of the encoder is that the predict value for one node is the joint probability of any other nodes in the same cycle, and the overall prediction is the joint probability of one node according to different cycles. The algorithm is to use constraint relationship between the base nodes and the check nodes in Tanner diagram to transmit and update the confidence information between the two kinds of nodes, and finally realize the decoding. The flowchart of the sum product algorithm is shown as following. In sum product algorithm, we convert the probability ratio into log likelihood ratio. The advantage of this representation of probability is to simplify the computing in the later algorithm, since the multiplexing took place by addition. The flowchart of the algorithm is in this form. As it is shown, every base has its own log likelihood ratio, and they all contribute to the check nodes and vice versa. The overall log likelihood ratio of the S base is the result of addition of its own log likelihood ratio and from other nodes with different probability weights. The matrix E and M is updated each iteration, and the result is more closer to the corrected code word. Here is a contrast of FDM and OFDM. The use of orthogonal subcarriers allows more subcarriers per bandwidth, resulting in an increase in spectral efficiency. In a perfect OFDM signal, orthogonality prevents interference between overlapping carriers. The block diagram of OFDM is as below. The concepts used in simple analog OFDM implementation can be extended to the digital domain by using a combination of FFT and IFFT digital signal processing. These transforms are important from the OFDM perspective because they can be viewed as mapping digitally modulated input data onto orthogonal subcarriers. In principle, the IFFT take frequency domain input data and converts it to time domain output data. The channel we use between the transmitter and the receiver is fading channel, different from addictive white Gaussian channel. The fading channel also takes the distance of transmit and the frequency of signal into consideration. Loss is the inevitable when a signal travels along a long distance. The function of the free space loss is as following. After introducing all the theory, we come to the discussion part for the performance with noise. A properly designed communication system should have no error in decoding. This graph shows the performance of system in the noise-free channel. Since the receiver receives the code word exactly as what the encoder produced, the bit error rate stays zero of all designed SNR. This performance indicated that the simulation is designed properly. As can be seen from the simulation results in the figure, the performance of LPDC codes is continuously improved with the increase of code length under the same signal-to-noise ratio condition. In the region of small SNR, the bit error rate is not improved by the increase of code length very obviously, but with the increase of SNR, the bit error rate of LPDC code is obviously improved. Generally, the bit error rate of LPDC codes increase with the increase of column width at the same signal-to-noise ratio. The reason is that under the limitation of the code length, increasing column width will reduce the sparsity of the check matrix to some extent. It can also be observed from the graph that when the column width is 2, the performance is the worst. It seems to conflict with our previous conclusion. The reason of this performance is that LPDC codes with large column widths get more validation information than LPDC codes with small column widths, resulting in more reliable decoding. Therefore, column width affects two factors, which are sparsity and validation information, respectively, and these two factors have different effects on the performance of the system. The simulation results shows that the performance of LPDC codes improves with the increase of iteration time under the same SNR condition. Bit error rate cannot be reduced infinitely with the increase in the number of the iteration. When the number of the iteration is large enough, increasing the number of iteration of LPDC code can only increase the time delay and complexity of the system, and its performance will not be improved, obviously. This diagram shows the LPDC coding in feeding channel. As can be seen from the figure, the performance of LPDC decoding is related to the transmission distance and transmission frequency of the communication. The longer the communication distance is, the higher the bit error rate will be. And at the same transmission distance, lower communication frequency will reduce the bit error rate.